Section 5.1 is on antiderivatives and indefinite integration. So this is the last chapter we're going to see in this Calc 1 course. And the idea is what we're going to do is take everything we did for the last 2 or 3 chapters, which was differentiation, and we're going to do it backwards. Okay, so for instance, I know the derivative of x squared is 2x. So what is it when I go backwards? If I tell you I have 2x, the question would be, what function do I take the derivative of to get the answer of 2x? Okay, so those are the concepts of what we're doing. And when we've learned all of our operations, first we learned addition, and then we learned how to do it backwards, which was subtraction. We learned multiplication, then we learned how to do it backwards, which was division. So we've learned derivatives, now we're learning how to do it backwards. So essentially we're going to learn all the rules that we learned before, but backwards, okay? Really important concepts, and the cool thing here is we realize while derivatives had extremely important reasons and applications, such as finding maximums and minimums, maximizing profit, minimizing average cost, things like that, right? We also find that antiderivatives, going backwards, which are also called integrals, also have extremely important application problems. So all we do in section 5.1 is, or in chapter 5, is we learn basic integration rules and basic applications. It isn't until calculus 2 where you start learning some really difficult integration techniques. So just an introduction to antidifferentiation, which are called integrals. So let's get through this together. It says antiderivatives. To find a function, and I'm going to call it the parent function, or capital F is the parent function, whose derivative is the lower function, okay, f of x equals 3x squared, you might use your knowledge of derivatives to conclude that. So the idea is we want to find the parent function whose derivative is 3x squared. And what you might conclude is that, well, heck, if we take the derivative of x cubed, we would get 3x squared. So the parent function who you take the derivative of to get 3x squared would be x cubed. And that's what that says, because the derivative with respect to x of x cubed is 3x squared. So it says the function capital F, the parent function, is the antiderivative of f. So whenever I say parent function, what I mean is the antiderivative of. And that's because I'm going to get sick of saying capital F and lowercase f, capital F and lowercase f every time. So if I say parent function, I'm talking about capital F. So a function, the parent function capital F, is an antiderivative of f if on an interval I, when f prime, the derivative of the parent function is f of x for all x in I. It says, note that capital F, the parent function, is called an antiderivative of f rather than the antiderivative of f. To see why, observe this. And so what it's saying is there can be more than one parent function. For instance, we just observed that the derivative of x cubed is 3x squared, but what we're saying is that is no longer unique. Consider the function x cubed minus 5. That is also a parent function where you take the derivative of x cubed minus 5, you still get 3x squared, so that would still be a parent function, right? They could come up with another one. How about x cubed plus 97? That is another parent function because the derivative of x cubed plus 97 is 3x squared as desired. So it says, in fact, all 3 of these are antiderivatives. In fact, any constant c for the function capital F of x equals x cubed plus c is an antiderivative. So what are they saying there? They're saying, look, no matter what that constant is, if you add or subtract a constant, remember when you take the derivative of that, it's 0. So if we know x cubed is an antiderivative, then we know that x cubed plus or minus any constant is an antiderivative. So there's not one single answer, there's always an infinite number of answers because we can always add plus c. So let's read theorem 5.1. It says if capital F is an antiderivative of lowercase f on an interval I, then capital G is an antiderivative of lowercase f on the interval I if and only if capital G is of the form capital G of x equals capital F of x plus c for all x and I, where c is a constant. In other words, all antiderivatives have to be equivalent except for adding or subtracting a constant. So if you have an answer that's an antiderivative and I have an answer that is an antiderivative, the only way they can differ is by a constant. So that's what Theorem 5.1 says. Using Theorem 5.1, you can represent the entire family of antiderivatives functions by adding a constant to the known antiderivative. For example, we know that the derivative with respect to x of x squared is 2x. You can represent the family of all antiderivatives of f of x equals 2x by, so what they're saying is if you take the derivative of x squared, you get 2x. So x squared is the parent function, right? So they're saying rather than just finding one parent function, we can find it in general by saying it's x squared plus c. So this is called the constant of integration. That plus c is called the constant of integration. It's the arbitrary constant, and that's how you have to answer all of the questions. So if they just say an indefinite integral, find the antiderivative, every one of your answers, when you get it, you have to include this plus c, the constant of integration. So a differential equation, which is a course if you're an engineer you're going to have to take. It says a differential equation in x and y is an equation that involves x, y, and the derivative of y. For instance, y prime equals 3x and y prime equals x squared plus 1. So what you are, a differential equation, is just an equation that has a derivative. That's really what a differential equation is.